All right, we're going to go ahead and continue our discussion. Now moving on to energy in the simple harmonic oscillator. So what we're going to do is first describe the conservation of energy. So this is going to be true for the simple harmonic oscillator as well. So we have that our kinetic energy plus our potential energy equals some constant, okay? And we can rewrite this as 1/2 mv squared plus 1/2 mx squared equals a constant, okay? And now if we want to look at a pendulum, a simple pendulum, we can rewrite this in the following terms. We have 1/2 ml squared omega squared plus 1/2 mg L theta squared equals a constant. So this is again my kinetic energy plus my potential energy equals a constant. So again, conservation of energy in both cases here. For the simple harmonic oscillator, we also have this diagram here to kind of show what we're talking about in terms of our energy. So remember that we have some equilibrium point, when we call that where x equals 0. Okay, and if we have this situation here as in part A, we have some sort of spring and we extended it with this mass on the end of it and then let it go. It will have a restoring force. Remember that F is our restoring force that will try to push this mass back to equilibrium, okay, back to this x equals 0. And with that, there's going to be some sort of velocity, okay, involved with that. And at the point where it is pushed back and it goes past the equilibrium, the system will hit its maximum velocity. This V max is going to be at equilibrium. Okay, that's going to be its maximum velocity. And it has some energy here, okay, some kinetic energy involved with that. Okay, so again, we started here, okay, where we've got a restoring force and therefore some kind of potential energy. Then as it goes to past the equilibrium point, it's going to have some kinetic energy. Okay, then when it compresses past the equilibrium to this negative x amplitude, it's again going to have some kind of potential energy. Note that in this figure it also says that the velocity equals 0 at these 2 points. That's because it is switching direction, okay, slowing to a stop and then going the other way again. And then we have again this midpoint where we have kinetic energy again with some velocity, V max, and so forth. Okay, so this shows you a full, let's say a full oscillation from this starting point all the way back to that starting point again. Okay, so this is the idea of the conservation of energy in a simple harmonic oscillator. This can also be represented as SHO. Okay. All right, so we can use this idea to find an expression for that maximum velocity. Okay, so if we start our simple harmonic motion with a 0 velocity and a maximum displacement, okay, like we did here. So if we start here, the total energy E is just going to be purely potential energy. Okay, and so the conservation of energy then will state this. So we have the kinetic and the potential is just equal to this energy here. I should put E. Okay, so from that, you can do some calculating and solve for our velocity here. Okay, and we can rewrite this. Again, this is just through some algebra. not going to go through the details of it. And a couple more things of algebra. And then we define our maximum velocity here. Okay, we're going to go ahead and just claim our maximum velocity is the square root of k over m times x. Remember that x is our amplitude. Okay. All right, and again, for the simple pendulum, just for the sake of knowing it, our omega max, okay, remember omega is angular velocity, okay, that's going to be equal to the square root of g over L times theta max, okay? Okay, so let's go ahead and do an example with this. Okay, this is example 16.6, and we want to determine the maximum speed of an oscillating system in a bumpy road. Okay, so let's suppose that a car has a mass of 900 kilograms and has a suspension system that has a force constant K equals to 6.53 times 10 to the 4th Newton per meter. And the car hits a bump and bounces with some amplitude, 0.1 meters. What is the maximum vertical velocity if you assume no damping occurs? And damping is sort of the same idea as friction in the sense that it will kind of slow down the system. Okay, it's a resisting force. Okay, so we're assuming that there's none of that occurring. So let's go ahead and use the ideas that we just found to find that maximum velocity. So that's going to be V max equals K over M square root times our amplitude X. Okay, so we're going to have the square root of K, which is 6.53 times 10 to the 4th Newton per meter, divided by our mass, which is 900 kilograms, times our amplitude, which is 0.1 meters. Okay, so then using our calculator, making sure that we get all of this correct in here, we can calculate this. So 6.53 times 10 to the 4th, divide that by 900, take the square root of that number, multiply it by 0.1. And we get that our maximum velocity is going to be 0.852, and this should be in meters per second. Now remember that we can always check to make sure that our units are correct, which is always a good idea. So here I'm going to go ahead and write this out. Kilogram meters per second squared, and that's going to be divided by m and a kilogram, and that's all in a square root times m. So we get the kilograms cancel, the mass cancels here, and then we have 1 over second squared inside the square root times meters, which just gives me meters per second, which is good. All right, so that's going to be our maximum vertical velocity of this car. Okay. All right, so let's go on and start talking about waves. So we talked about them or kind of mentioned them earlier, but we're going to go ahead and talk about them a little more. Okay. And one thing about waves is that we need to know what they are technically. When we think of it in our head, we kind of think of like waves of the ocean, right? Bad drawing, but you get the idea, okay? And what waves really are is any kind of disturbance that propagates or moves from the place it was created, okay? So take an example here, dropping water droplets into a body of water or a rock like we talked about earlier into a body of water, okay? It creates these ripples, okay? You see this little ripple here, okay? These will propagate 360 degrees. So it propagates all around. So you get like these ring patterns. Whoops. These ring patterns, right? Okay. I'm going to erase that. Eraser. Okay. So you get those wave patterns, and we can describe that motion. Okay. And that's with the oscillatory equations that we looked at earlier. Okay. And to describe a wave velocity, we can say that the velocity of the wave equals lambda over our capital T. What is lambda? Lambda is called a wavelength, okay, which is the distance parallel to the direction of propagation. What does that mean? So basically, from high point to high point, what is that distance? Okay, if we're looking at a wave like this. Okay, and divided by our period. Okay, this can also be equal to our frequency times our wavelength. Okay, so again, it's from peak to peak. That's how I like to think of it. The wavelength is from peak to peak of waves. Okay, and so when we're looking at this, I guess not when we're looking at this, but just understand the idea of what a wavelength is and how to calculate that wave velocity. Okay, so we could use this to do another example. This example is 16.8, stating we want to calculate the wave velocity of the ocean wave in the figure if the distance between wave crests in this figure is 10 meters, and the time for a seagull to bob up and down is 5 seconds. So, okay, so we have some kind of distance between the wave crests. Okay, so that's like what I said, from peak to peak. That's going to be our wavelength. So our wavelength is then 10 meters. Okay, but what is this? The time for a seagull to bob up and down. Okay. So for this seagull to go all the way up and then all the way back down, it says it takes 5 seconds. So is that our frequency, or is that our period? Think about that for a second. The time it took for the seagull to bob up and then back down. Okay, so hopefully you guys thought about it a little bit. If not, that's okay. But the time it takes for this seagull to bob up and down means that it is the period of this wave. Okay, so basically it's saying this, the time it takes for one wave to go up and then back down. Okay, so my T is 5 seconds. Okay, and we want to know the wave velocity. So remember, that's going to be lambda over T. So lambda is 10 meters. My period is 5 seconds. So 10 divided by 5 is 2 meters per second. So this is my wave velocity in this case here. Okay? All right, so in the next video, I'm going to talk about types of waves. So I will be back in the next video talking about that and then showing you a couple more examples.